Okay, this one is Giancoli Physics AP Edition, 7th edition. We're in Chapter 10, Fluids, and we're working on problem 13. Go ahead and jump in. That problem reads, in a movie, Tarzan evades his captors by hiding underwater for many minutes while breathing through a long, thin reed. Assuming the maximum pressure difference his lungs can manage and still breathe is negative 85 millimeters of mercury. Calculate the deepest he could have been. Okay? The idea here is, and the reason it's a negative pressure, if he's under the water, breathing through a reed, basically a straw here, the pressure in the entire tube here is roughly atmospheric pressure. And so if he's breathing down here, he's got to breathe against the pressure difference created by this column of water. So go ahead and wrap your brain around this problem, see if you can come up with a plan, pause the video, come back when you're ready. Okay, using our problem solving strategies, we know we're dealing with a pressure here. Again, this is one of the odd units of pressure that you may not be familiar with, often used in meteorology to measure pressure this way, millimeters of mercury. They're asking us for a depth, which is basically the height of the column of water here, and we have a pressure. So if we look at our available equations to deal with those quantities, grab our equations from our equation sheet, or your textbook is the case may be. And again, because we're dealing with a differential pressure here, we're not really looking at the total pressure. We're going to zero in on this equation here, or differential pressure or gauge pressure is the density times acceleration due to gravity times the height. The height is the thing we're looking for. We have the pressure, that's the number they provided. We know the density of water from table 10.1 in this chapter, or you can search it with your search engine. Acceleration due to gravity on whatever planet, assuming Earth, we're going to calculate the height. So this is a relatively simple rearrangement. The height is going to be the pressure divided by the density and the acceleration due to gravity. At this point, we're ready for the plug and chug. As you might suspect, with this slightly more exotic unit for pressure, we're probably going to have to do a unit conversion. For that in a moment. For now, the pressure we have, I'm going to drop the negative because I'm just worried about absolute value here. We have 85 millimeters of mercury. And again, that weird unit is based on how many millimeters of mercury that pressure would hold up. Divided by the density. For water, the density is 1,000 kilograms per cubic meter. And as always, on Earth, acceleration due to gravity is 9.8 meters per second squared. Go ahead and plug that in. I'm going to give myself a little bit of room for the unit conversion. Now, if you're operating out of Giancoli, there is table 10.2 in this chapter. Now, pressure is one of the more generous quantities in physics as far as the number of units available to us. Here's table 10.2. If you're not operating out of Giancoli, your book may have a similar table, or you can always search this on the internet to find the conversion factor. We're dealing with millimeters of mercury, which again is the column of mercury this pressure would hold up. If you look over here at 1 atmosphere, any equality will work to generate a conversion factor. If you've studied unit conversion with me, you know this. But for me, I'm going to use a conversion for pascals in millimeters. So if we look at millimeters of mercury, here's 1 millimeter of mercury is equivalent to 133 newtons per square meter, which is our pascals. So that should work for us. In this problem, our millimeters of mercury is in the numerator. So I'm going to put my 1 millimeter of mercury in the denominator, so those cancel. That'll leave me with 133 newtons per square meter in the numerator. This is the number 1. It does cancel my millimeters of mercury. It will leave me with newtons per square meter here. In the denominator, I have kilogram meter per second squared between these two units. That's my Newton that will cancel here. And then I've got per cubic meter in the denominator. But with a square meter in the denominator here. So this effectively is a cubic meter divided by a square meter when you're all said and done. That'll leave you with a meter, which is an acceptable unit for height. Before we pick up our calculators, we'll do some mental math. This number here is a bit less than 100, while this number here is a bit more than 100. So let's just call that 100 times 100. That's going to give you 10,000. Down here, you have 1,000 times 10. Again, it's about 10,000. So we should expect a number right around a meter, give or take. So let's punch our numbers in and see if we get, see if it makes sense. So your calculator should have produced a number similar to 1.1536-ish. Again, this is approximate meters. Given our significant figures of 2 here, we're going to round this to a more appropriate precision of about 1.2 meters, which checks with our mental math. That's a reasonable number. And this problem is done. We're on to the next.